electron, the magnitude of the charge of an electron. So that's that. That's the Helmholtz energy. What else I want to say about that? Oh. We can talk about the energy itself, which of course is this, which we saw before. We get this term from the translational part, right? We saw that earlier. And then there's going to be something for the electronic part, which I'm not going to go into, but you would have to take the logarithm of that and the partial with respect to t of it. Okay. So that would be the energy. So I guess the point is that the bulk of the energy comes from translation, but there's a little bit from the electronic. It's not very much, but it's there. Okay. Actually, maybe it's worth writing out. What would that be? So that part took into account the n prime. I believe we get within our approximation. You can go check it out. That's what I have written down. So that's not what they have in here. Delta E. And then there are other terms. So what's the point here?
No, we're still concerned with the change in energy, not the actual value of the energy.
No, this is the actual value of the energy.
You're saying that translational energy is much larger than the electronic energy?
So let's see here. What do we have? This is KT. Here we have the denominator Q electronic, which is all of this. We took the logarithm. How did they get there? They took a logarithm of this part right here, which is n log all of this. Let's see. There's a KT symbol. Let's see, how would they have gotten there? I'm thinking about how they got here because I haven't done the math. But what you need is it's minus KT times the logarithm of and then they simplified that in some way. Oh, wait. I'm talking about energy now. I'm talking about energy. So we need the partial of this. I'm sorry, it's KT squared. It's the partial of that with respect. So that will be KT squared all over Q electronic 1 times the partial with respect to T of And the temperature dependence is right here. So that's where, and the partial with respect to temperature will give you the delta E out in front. It will get rid of one of the T's here apparently, and the K as well. So that that's why the K's gone and T's gone. You got this. Yeah, you get the T squared is going to cancel the T squared. The K is going to cancel the K. And you get the delta E out in front. Now, why do you have the omega? Is that a mistake? Oh, that's an omega E2. That's why. That's omega E2. Okay, so that's that.
Now, I guess a qualitative way of looking at this in regards to comparing the energies. So, I guess just the kinetic energy is always going to be much larger than the electronic energy, or like what you were saying earlier.
Well, let's just think about it here. The 3/2 doesn't matter. The n is in both of them. Now you have the temperature here that you don't have here. So that's going to be a significant factor at room temperature. It will depend on the spacing of those energy levels. Oh, I don't know. I mean, the way to do it is to just calculate this for something.
Just depends on the temperature.
Just calculate it for fluorine. See what it is. For fluorine, Q electronic, you need this, and you need this, and you need that. You can calculate Q electronic easily. See how important that is relative to that for fluorine. That'd be a nice exercise.
Would the energy be the equivalent of the energy it would take to strip off the electrons?
Not exactly. Not exactly. Because when you, but close to it. When you strip off the electron, all the other electrons reorganize. So it's not, the ionization energy is not the same thing as the energy level. It's not. Now for the other atoms like hydrogen and helium, this exponential is just very, very small. So for most purposes, this will be a lot less than this. But you have to do it for one thing before you can really see, you know, if it's true. But there's another way to think about it. As for most atoms, if you have for most monatomic gases, if you have a large collection of them, they're almost all in the ground state. So the energy is going to reflect the ground state. Now the last thing I wanted to mention then is the entropy. Oh, maybe no. I want to mention pressure too. So that's the pressure. It's kT times the partial log Q with respect to V. And when you look back at Q, the V dependence is only one place, and it's there, right? So when you take the log of Q, and then you take the partial with respect to V, everything else just drops out, and the partial of right, which is the perfect gas equation. I forgot the N. right? So, so that's cool. Again, oh my God, that's amazing, isn't it? Well, you're going to get that answer no matter what everything here is, as long as you got v to the n, right? You've got a v to the n. Doesn't matter what everything else is, you'll, as long as the partition function is some function of temperature times v to the n, you'll always get that answer. Right? So it's not quite as amazing as it seems at first, but the perfect gas equation is a natural consequence of this. Then the last thing I want to mention is the entropy. Which you can write this way. Notice that energy is kT squared partial of log Q with respect to T. So this term is really simply equal to E over T. So that's our familiar E over T. So S is K log Q plus E over T. That's what that is. So you can plug and chug. So what's going to happen? If we do K log Q, plugging in our expression for Q, let's just think about it before we do anything. We're going to get one term that comes directly from this translational part of Q, right, to the n, all over n prime. And we'll get another part then from the electronic part. Now when we take the partial of log Q with respect to temperature, we've already seen what happens. Because it's a logarithm, everything goes away except t to the 3/2. We get a very simple thing there. And over here, the temperature part is only present here. We've really already done the individual parts. So it turns out, what you get is three halves nk. And the 3/2 nk comes from the partial of log Q with respect to t, this part where the t is. That's the 3/2, obviously, and there's the n. That's that one. Plus now this term comes from K log Q, the translational part right here, and the V also comes from translation. Remember the E over the N comes from the n factorial part we saw earlier, expressed in this curious way. So now we've got the translation here, and then I'm not even going to do any work on the electronic part. It's usually less important, but you can do the work on the electronic part. You get some S electronic. Now, this equation is quite famous. It has a name, the Socratic equation. And I think it's interesting to see how it does for some substances. It's, if you look, you often see this written in introductory textbooks to physical chemistry. And you look, it's like, God, where all that come from? Pi, K, M, E, N. But you can see it really has got a straightforward derivation. And if you look at page 86, they've got the result of the Sacred-Trodi equation for a number of monatomic gases. They compare the experiment to the calculation. And by calculation, they mean just plug in the Sacred-Trodi equation. And you see they do pretty well. Really quite well. Then you might say, wow, that's really cool. Of course, remember, there's no vibration, there's no rotation. This is just something that's very well described as a point particle running around in space and not interacting with anything else to a very great extent.
But then it also has an asterisk that says the experimental values have been corrected for any non-ideal gas.
Oh, the asterisk.
Yeah.
I was just wondering, I was going to look and I was going to say, I bet helium and neon do better than mercury. And that's because they corrected for non-ideal behavior. Well, that makes it less impressive, doesn't it? What the heck does that mean? What the heck does that mean?
I mean, they took the experimental result, subtracted that from the theoretical part, and said, well, this must be the non-ideal part.
What else can they be talking about? Why do they bother with that? They got rid of any nuclear contribution, I guess. That makes it much less impressive. I kind of want to pretend they didn't say that. We need a table that includes the non-ideal part.
Well, I don't know what they did.
What would they be? I mean, we did that, conversion of the sum over states to the integral to get the translational part, but we know that translation is virtually continuous, so that's hardly an approximation.
Maybe they calculated the probability of near collisions and factored out some fraction.
But it's experimental part.
Hmm.
They changed.
Yeah, no, exactly. So you get an
How do you-
experimental result,
And you
but you
subtract
think
one part.
about what the probability of
A collision's an interaction, right?
Yeah.
So,
some small fraction of the result they remove.
It's possible.
well, it'll be very interesting to see for those same gases how well the Sacred-Trodi equation does relative to the actual. I mean, it would be fun to see how it does for the noble gases. I would think it would do pretty well, but that was less impressive. I think that's all I wanted to say. I mean, this chapter is really a one-week chapter, a one-day chapter. I mean, because talk about term symbols wouldn't be sensible. I guess I didn't talk about the chemical potential, but that's, you can read that on your own. That's just the mu is minus kt times partial log q with respect to n. Well, you can take that partial derivative. So that's really that. That's the most straightforward application of our formalism. So we started with that. I think I will next time start with the next chapter on the diatomic gas. Okay. If I look ahead, by the way, to the exam, because maybe I should wait to talk about that until the others are here. Because I have, this week is the 18th and the 20th, that's supposed to be chapter 5, but the 18th is all we needed for chapter 5. So on Thursday we'll start chapter 6. Next week was set aside for chapter 6. And yeah, we'll need like 1.5 class periods on it. I was gonna set aside Thursday for any review. That would be Thursday the 4th of October. Then the 9th of October is a Tuesday and I'm not here. And so Thursday was gonna be the midterm. And then after that, we were gonna start chapter 7, which is classical statistical mechanics,
Thursday,
stat thermo. But the way I'm looking at it, if we start with chapter 5 on the 20th, if you want to see, if we start with chapter 5 on the 20th, that's this Thursday. We'll finish it on the 25th.
Well, we just finished chapter 5. We just finished chapter 5.
So maybe finish chapter 26, I'm sorry, chapter 6 on the
Oh,
25th.
you're right.
When we like to speed of light.
So if we start chapter 6 on the 20th, diatomics, we're going to finish it on the 25th. And that will allow us on the 27th and 2nd to do the classical stuff
Yeah.
and have a review.
The classical stuff doesn't have its own chapter, or is just something on the side?
It's chapter 7.
Oh, chapter 7, okay.
I see what happened. Chapter 2, I set aside 3 days, but we only used 1 day. And then for chapter 5, I set aside 2 days, but we only used 1 day. So we got a week. We got a week back.
So test is like.
So we could either have the test earlier, but I kind of like the timing of it, because I'm going to be gone. That gives you a day for studying.
Keep the pace up and just do December off.
There we go. This is actually good because it means we could do a little more non-ideal stuff later, which is, I think, gratifying. We could do more condensed phase than I did before. I think what we should do is cover the classical stuff, chapter 7 before I leave, before the test.
But it won't be included on the test, right? Or will it?
I think, I'm tempted to say not, and the reason I say that is I really want you to get the basic stuff down, and then the monatomics and diatomics provide applications of the basic stuff. I think we'll cover the classical, but it probably won't be. That was my whole idea in the first place, not to have it on the test. I kind of still want that, I think.
So we're thinking the test on October 4th, or
No, we're going to stick with the test on the 11th.
11th? Okay.
Because I'm going to be gone on the 9th, and